What makes a journey a discovery? Well, it starts with a first step, an often unlikely beginning, driven by a force that makes us question our world. Understanding that there is something to be found in everything, in everyone, that around us are little universes waiting to be unlocked if we look a little closer, question a little more, and try a little harder. And that the questions of doubt are the fuel that force us to continue, to struggle on. The risks are the reasons, and new possibilities are inspiration. The journey is greater than ourselves. And that when we finally look back at the unlikely heroes, the outliers, the disruptors, we understand that it is the people who question, who look a little closer, that are the ones that drive innovation. Celebrating the spirit of innovation.
And please welcome the Dean of the College of Engineering, Nadine Aubrey.
Good afternoon and welcome everybody. I'm sorry that the room is too small, it looks like, but I was told by our guest that this is nothing compared to what happened to him in China, where for a 10 o'clock lecture, people were in the room or in line to get in the room at 7 a.m. So anyway, this is my great distinction and pleasure to introduce Sir Harold Kroto, the 1996 Nobel Prize in Chemistry that he shared with Robert Curl and Richard Smalley. Kroto, Curl, and Smalley received the Nobel Prize for their discovery of a new molecule, the C60 molecule, which was the first fluorine molecule to be discovered. Fluorine, as you all know, is the third well-defined form of carbon, the other two being graphite and diamond. So not only it was a great discovery to discover a new molecule, very exciting, but yet it was really a paradigm shift due to the applications which were going to succeed. And tremendous applications followed in the areas of material science, electronics, and nanotechnology. This was done by Harry while he was at the University of Sussex in England. Since then, in 2004, he joined Florida State University as Francis Epps Professor of Chemistry. Professor Kroto not only received the Nobel Prize for his outstanding research and discovery, but he also has been involved in a large number of advisory boards, as you can imagine. He received not only one honorary degree, which is a good thing for all of us to get, but he received 40 honorary degrees at universities around the world. He's also a foreign associate of the National Academy of Science, which he was elected in 2007. So welcome to Sir Harold Kroto to the Northeastern Presidential Profiles in Innovation series here at Northeastern. Please join me in welcoming him for his talk on carbon in nano and outer space. Welcome.
Thank you very much.
Thank you.
Well, it's a pleasure to be here, and I'm sorry you're going to have to stand, but I've got to stand too, so don't feel too bad about it. I've got to give this talk. I am going to talk a bit about this molecule, and thank you, Eric, I guess, and Amit for the invitation to come to Boston, a town that both Margaret and I, who's here, like very much. Okay, that's not loud enough. I'm going to give you this. Just let's see that. Let's go back there. Okay, get that off. Go on. Okay. That's right. That's a bit better. Okay. That's to wake you up, just in case you've gone to sleep. It might happen occasionally during the talk, so beware. All right. It's a pleasure, as I say, to be here. I had a life before C60, believe it or not. and it was in flash photolysis. And I thought I'd show you George Porter, who was my professor at Sheffield, and I thought I'd show you what we used to have to do. Basically, quartz cell, a spectrograph, trigger, spark gap, high power flash lamps, photocell, delay unit, and spec flash capacitor and spec flash. And what you did then, you filled the quartz cell with a compound in this kind of bromoform, charged up the capacitors, and then triggered that. A flash produced a free radical CBR, and then through the delay unit, it set off another spec flash. The light went through there, and you got the spectrum. That's how this is a major breakthrough, and George Porter got the Nobel Prize for that. And that's how I started off in research. And I thought I'd show you my first ever result. And I'm sure that many of you are researchers, you've always had the first result, and then you discovered it had already been discovered before. And this was my first result that I discovered hadn't been discovered before. And I looked at this and I thought, well, it looks interesting. And then my supervisor, Richard Dixon, came, look at this, and blew this up. And I saw these lines, and that was the cathartic moment that really went on. Once I saw these beautiful lines, I thought, this molecule can count a lot better than I can, because of those lines were there. So that was my first result, and I was then hooked on doing research. But then I went on to do microwave spectroscopy, and we created a whole new set of molecules, carbon double bonded to sulfur. We made the first carbon-phosphorus double-bonded species, and a whole set of those, and we created the field of phosphoralkenes and phosphoralkyne molecules. When we made these, only HCP, that one was known. And then there were the boron sulfides. And then these two molecules at the bottom turned up. My favorite molecule in some ways is this one, because we made the first carbon-phosphorus double bond. I guess in some ways the one molecule I love most is this one, nitrosoethane, because it looks like this. Now, does it look like anything to anybody? Anybody? Yes, it's my dog. Made of, okay. I look at the microwave spectrum, I discover the dog shakes its head, and it looks at its tail. Not only that, the dog's really quite an interesting one because it can undergo internal rotation. It's been drinking, something I don't think many students on campuses here can do, but the dogs can do it. And if you've been drinking too much, you know what the problem is. You desperately need a lamppost. Now, the reason for showing you this is that I want to impress you on that I think the 21st century is the century of molecules with function. Molecules do this. The problem with carbon dioxide is not that it's carbon dioxide, it's because it vibrates. It's its flexibility and its dynamic properties that absorb infrared radiation. So think about that. And in fact, that started me off because I was fascinated not just by the vibrations of carbon dioxide, but by the vibrations of long carbon chains. And the spectrum that started the ball rolling was this molecule, HC5N. Basically, here is the precursor, a trimethylsilyl compound, and when you cleave off the hydrogen, you get this molecule. And a rotating dipolar molecule generates a radio wave, or you can absorb it, okay? But how was that made? Well, it turned out I was very, lucky that my friend and colleague, David Walton, was the world's expert at stringing carbon atoms together. He'd made a chain, a linear chain of 32 carbon atoms. And how had he done that? Is by a copper-catalyzed oxidative coupling reaction in which the oxygen takes away the two hydrogens and brings these two like a train together, okay? Nice and simple. And we made the first molecule, which is this one, which led to discovery in space. Now, it turns out at the same time that Charlie Towns, who basically developed the maser and laser, started to look at what was going on in space. And I thought I'd show you Bill Klemperer, who is not very far away, professor of physical chemistry, some of you know, at Harvard.
I've told you, and you have to believe that I tell you the truth, that carbon monoxide is the second most abundant molecule in the universe. And yet our theory, our equilibrium theory, says there shouldn't be one molecule in the whole universe. It's that extreme. What does this say? Well, it doesn't say that thermodynamics is wrong. Of course it isn't wrong. That's impossible to be wrong. It says that it's totally inapplicable to the chemistry of the interstellar medium, that everything is dynamical, that in a sense, it very much resembles the Earth. If you ask, what is the equilibrium status if everything is quiescent? Everyone's dead. That's it. And very uninteresting. So we would like something much more dynamic than the thermodynamic equilibrium. And I should say, as a testimony, really, every time I mention that to a group of college students, the audience breaks into tremendous applause if thermodynamics is not applicable. And I wonder why. It might well be that it's so poorly taught that just to like it, that it doesn't work.
Anyway, one of the greatest lecturers was Bill Klemperer. How many of you know Bill? Just to see you know what I mean, if you've ever seen him. My student said he could recite the telephone directory and you'd enjoy it. Anyway, he's talking about interstellar space. So in the late 60s, early 70s, and the 80s, space became interesting. And particularly interesting was Sagittarius, where the molecule Hc3n had been detected, and we just synthesized Hc5n. So I wrote a letter to my friend Takeshi Oka, who we'd been postdocs at the National Research Council in Canada, and I said, I've got this molecule, and Takeshi wrote back, and I thought, thank you for your letter, yes, double exclamation mark, yes, I'm very, 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 very much interested in your molecule. The same number as berries as there are carbon atoms in this thing. Anyway, it turned out, yeah, we got together, and we detected it in space. So let me tell you a little bit about radio astronomy. Basically, with this telescope in Algonquin Park, and you can see, and you're familiar with the weather in summer in Canada, I'm sure, as you can see it here. You know what I mean here in Boston too, I think. We're a 46-meter dish, and the receiver is in this little room, and you can walk into it. And if a molecule is rotating and has a dipole moment, it can give out a signal, and you can measure that frequency to about 1 part in 10 to the 8th, very, very accurately. And we were able to show that in space there were carbon chain molecules, in particular in a part of the Taurus cloud, which is shown here. So these we detected around the mid-70s to the early 80s. Now, what happened then, I think, I wanted to give you a feeling for what it was like. In the HC7N one, I left the UK. Colin Kirby was doing the measurements, and I was on the telescope, and he phoned my wife, Margaret, who's here. Okay, there she is, her name, careers advisor here, and said the frequency, and then Margaret telephoned friends in Ottawa, and he phoned the telescope, and we reset this thing and basically had the most exciting time of my life because we had all the signal. And this is before we had computers, really. The computer could it wasn't enough. Now, this computer could run the telescope and do all of them, but in those days it wasn't possible. And so somewhere in this, and we knew that the central channel should be high, and it would go up and down like this. And basically, every time it was high, we would cheer, and every time it was low, we'd groan, and out of every 5, it was high 4, and then suddenly we saw this signal when we sort of synthesized the signal over several hours. That was the most exciting day. It may have been C60, but it wasn't. It was this particular one. And then we got HC9N. So that's it. And then the media got hold of it. Okay, now, you know, I don't know about you, but this gives you an idea what happens with the media. Well, first of all, you get your photograph taken. I show this because I used to have some hair, believe it or not, here. Just to prove it, there's Takeshi, Lorne Avery, Norm Broughton, and John McLeod. We had to have astronomers to point the telescope at the sky, you know, because chemists are always looking down in the dirty, grubby stuff, and physicists are looking at the bright stuff. And it turns out that the dark areas of space are very important. Space find. NRC probes 300 light years and discovers a new large molecule. And then here we are. I always hate this picture because I must get rid of this hair hanging down the back, like a hippie. They got in. They have discovered proof that there are organic chemicals in the vast dust clouds between the stars. Only one simple step would be needed to change these chemicals into the building blocks of life, you know. The interstellar DNA, and this is the best one. Chemicals were discovered thanks to Canadian work in radio astrology. Okay. That's the newspapers for you, right? Okay, there you go. Anyway, now that was important. And then in 1984, I visited Austin, and after the Austin conference, that Jim Boggs, who died just last year, he always used to get me money to come to this conference. A really wonderful guy. He used to get me a few $100s, and with that few $100s, I could get the Royal Society, someone else to cough up a bit more to go to this conference every 2 years. But after one, I was invited by Bob Curl to visit Rice University, and he showed me a paper by Rick Smalley on SiC2. Now, this is interesting because C3 is more or less linear, but the silicon is right over here. The structure is really very interesting. And there I met Rick Smalley. Okay, and Rick was jumping all over the apparatus and was really a brilliant guy. And he developed a nozzle, a magnetic pulse valve. And if you show it here, a laser goes through this hole and a magnetic solenoid valve opens and shuts and lets helium through here. Okay? And what he was doing was, as the helium goes through, he would fire a laser and produce a plasma from what's inside the nozzle, which would go through this skimmer into a mass spectrometer. So basically that's it, okay? Let's do it a bit more slowly. It skims it into a beam into the mass spectrometer. And what he was looking at was, at the time, I think was something like aluminium, and producing aluminium clusters. And whilst he was jumping around, very excited because it's a really big breakthrough in cluster science, I thought, well, why not change this to graphite, and maybe we could produce the carbon chain molecules that we detected by radio astronomy, and therefore simulate the conditions in a particularly interesting star called IRC 10216, in which the carbon chain molecules had been detected. We detected them in the cold parts of space, but in fact they were discovered streaming out of this particular star and other stars. So the idea was, well, let's vaporize graphite and simulate the conditions in this star. That was a simple idea, and I knew it would work, okay? So basically that. Anyway, about a year and a half later, I got a phone call from Bob. He said, we're going to do this experiment. Are you coming? And I thought, well, yeah, but here's a little bit of a thing. I was also interested in going to half-price bookstore. It wasn't just, to do the experiment. There are other things as well. And I want to impress on you that, science isn't just focused science. You have to have some other things in your armament, and we'll see what that was in a little bit later. So another reason for going back and doing this experiment was that there's a really great half-price bookstore, which I loved going to. When I arrived for my second visit in 1985, there were Jim Heath and Sean O'Brien and Yuan Liu were the students that I met, and we worked together, and we found the carbon chains, just as this was exactly what I expected. I expected to produce these carbon chains, and that if they were carbon chains, they would have two reactive ends, and in the presence of hydrogen, would put two hydrogens on them. That's what you exactly. So this is the next lesson. I knew what to do. I knew it would work. It worked exactly good, but I wanted to make sure it went that way, okay? What I didn't know was, of course, there would be something else there. And Sean had improved the nozzle configuration. These are some of his drawings, which, was a very... And what happened was that as well as these small carbon changes, here's the mass spectrum at time of flight, there was a massive signal for C60. And this guy is telling us, look, you guys, I'm the most important guy on the block. C60 and my little friend here, Sancho Panza, okay? I call it Don Quixote as Sancho Panza here. C70, we're far more important than these guys down here, C11, because we had detected 9, and these fellows, and C11 had been detected. And this was well known. This particular pattern, 11, 15, 19, and 23, has been known since the 60s of carbon chains. It's very interesting and implies, and I think now good evidence, that these are monocyclic rings of carbon. But this was new to us. And I wrote on my printout C60 huge, C70 also. And in fact, about 2 days after that spectrum, Sean found that he could actually get the signal 60 times larger than anything else, okay? And in fact, the next day, Jim got it 40 times. So this was the final thing that was published, that here is the spectrum of C60. And it's clearly saying there's something interesting here. And the only thing you really have is structure. It's got to be something beautiful or somehow like this. So that was it. And the question is, what was it? And of course, many of you probably know that it was we suggested that it was the C60 molecule. It was Buckminster fullerene. Well, how would we prove it? These are two students, Amit Sarkar and Jonathan Hare, and we had this bell jar evaporator, and here's Jonathan adjusting the gap. And one day he put this red solution on my desk. Now, I want to tell you that at that moment in 1990, to take graphite, that's what it was, and just put a discharge through it, and then get a soluble sort of system was pretty unbelievable. I know you youngsters don't believe it, but it was. So I'm looking at this thing, this red solution, and thinking, this is 5 years gone by now, bothered about these sort of things. So that was put on my desk, and basically on a Monday. On the Friday of that week, I got a call from Nature, and that's the journal. And they wanted to know whether I would look at this paper. And I couldn't see the hurricane coming. 12:05, a fax came in. Black Friday. Okay, solid C60, a new form of carbon, a fantastic paper by Kretschmann, Lamb, Fosteropoulos, and Huffman. And as I read this whole paper through, there was a fantastic images of a molecule which the X-ray structure said was, looked like spheroidal molecules. And I read this paper, and wine red to brown solution here, liquid brown, and this is sitting on my desk for 4 or 5 days. Oh, shit, okay. Right. Go for lunch or commit suicide. These seem to be the only alternatives. Well, I don't know what it's like here for food in the university, but going for lunch at Sussex isn't a lot different from committing suicide. Anyway, I went for lunch, read the paper through, and thought, I'll ring up. Nature said, fantastic paper. Congratulate Kretschmann or Wolfgang, who I knew. There's a lot of other things I don't have time to talk about because it's a beautiful paper. I consider the Kretschmann-Huffman paper one of the greatest papers in the whole of chemistry. By a couple of physicists. Bloody irritating, I tell you. But it is a very, very, very good paper. Anyway, one thing was missing, and there was no NMR spectrum. And I knew that one thing I dreamt about was that C60, all the carbon atoms are equivalent, and therefore, with one line, you should be able to prove its structure, because they're all equivalent, should all be in the same place. I had this dream. And I could show it to my colleagues with, the 60 carbon atoms, just one line would prove the structure. Anyway, Tony Avent, our NMR guy, sort of called me up and said, you come down because I've got something interesting to show you. And he showed me this fantastic single line. He said, there's only one problem with this line. It's benzene. And it's been done. Okay. He said, but if you look here, so I had to get a magnifying glass to see this thing. And this ugly little thing, the ugly duckling. I mean, it's like a parent. It doesn't matter how ugly your child is, you love it, This is the first spectrum. I love this spectrum. It's the first NMR signal of C60, which was the proof that it was the molecule we said it was. So that was basically some part of the story. I'm going to jump on a little bit because just to say one or two things, we did a lot of work after that. One thing that I was interested in was the mechanism of forming nanotubes, okay? And I wondered about this because we started to work on these, and there were interesting structures like these closures that looked as though they were basically nanotubes with a closed end. And I wondered whether basically, if you looked at this, the central core under an electron microscope, you could see something. Here, for instance, you see that little igloo. It's actually a graphene igloo. And I thought maybe surface reconstruction of a crystalline carbide would lead to segregation of a graphene sort of sheet from the top. And that was quite a long time ago. And what happened then was that Umberto and Mauricio Terrones, Mauricio had worked with me, two fantastic young Mexican scientists working with Florian Banhart, got some evidence that this idea was correct. Now, if you think of a three-wall nanotube like this under the electron microscope, then the cross-section will look like this, and that's what we've got. We've got a multi-wall nanotubes and a metal carbide in the center here, so an iron catalytic particle. And now watch it. It's got a flat meniscus, but do you see it's now pretty flat, and now it's much more curved. Do you see that? And then if you look at it, well, there's a line turns up here. That is the birth of a nanotube in a metal catalyzed particle. And here we see waves of these coming out of the metal particle. So you're actually seeing in situ, under the electron microscope, the birth of a multi-wall nanotube. Okay? So that looks as though it's a good idea. Then I want to show one other aspect of young scientists, and this is that it's an international brotherhood and sisterhood. There is nothing else, no other group are linked together as the international scientific community. It doesn't matter what color you are, what nationality you are, what religion you are. What we're doing, we're working on the way the universe is. It's the way that it wasn't created by us. So we have a bench line of truth, and this is what links us together. This is the rogues gallery, and notice we're a little bit worried about sort of Wahhabis in Syria. Anyway, a favorite picture taken by Margaret, shown here, is this little boy totally engrossed in making a buckyball. And I was playing around with this and trying to make the molecule C32. There were some interesting aspects of C32. And when I built it, I discovered it wasn't C32, it was C28. And I remember my hair standing on end. I thought, gee, C28. We've got a strong signal for C28. C28 is a bit special. And I then played around with it and realized that yes, it is special, because if you add 4 hydrogens to this, then the carbons would be sp3, and that would relax the outer plane strain at that atom, but it would also retain the aromaticity of 4 of these. And I thought of this as a superatom. It's basically an atom, made a cluster atom, and it should be tetravalent. Anyway, that goes on, and I thought, well, go on now to basically, I ended up in Florida, Florida State, not the University of Florida, just to make sure, because, there's a bit of trouble between these two. Well, at least on what I don't know what game this is, but it can't be football, because they don't use your feet. So I think you should rename this game. I mean, there's only one guy who's allowed to use his foot, I think, and you call it football. That's not the only thing funny about this country, I must admit. Anyway, anyway, to cut along, I think you only took it away because you wanted to call football. And anyway, to cut a long story short, here are some of my... Steve Acko, fantastic guy, parents from Ghana, came with me to Florida State. Daryl Ventura, archery span, Prashant Jain from India, Nicola from India, and Paul Dunk. This guy is Paul Dirac, and I wish he would come into the lab because we really need his intelligence in there. But there you go, he sits out in the Okay, so... started to work on this again, and actually about 93 or so, Rick's group showed that uranium could be put on the inside, and that my idea 5 years earlier, that C should be tetravalent, looked as though it was a good idea, and you could satisfy the valency from the inside. Well, with Paul Dunk and Alan Marshall, we've been looking at this, and you can put titanium, and it stabilizes it, okay? So the various spectra that we've been looking at now, we've gone back to these problems, and with potassium and first group elements, basically C60 and C70 are the most stable in the gas phase. But if you go to group 2 metals, what you find is basically that's C50 and C60, okay? It looks a bit like Batman to me, but there you go. All right, so then we look at group 3 metals and C44. So you're stabilizing other species by putting different elements on the inside, and this is really quite interesting. And if you've done all the lanthanides now have been done by us, and by Paul actually, has shown that there's something interesting in this, and maybe in the future we'll be able to extract those. And we have fantastic resolution. Alan Marshall has developed the ion cyclotron resonance Fourier transform mass spectrometer. And so we can easily separate things like C32 from titanium C28, titanium mass 48, which is, I hope, as you know, is 4 times 12. All right. But uranium is interesting, and I'm just going to show you this. This is the laser vaporization of uranium. And you'll notice that here, as we vaporize this and go to different laser times, uranium C28 is massively strong, and it's easily the first gateway species to the higher ones. So there is something very special between titanium, zirconium, uranium, and carbon in the case of C28 cage. All right, so that's part of it. Okay, so let's now go on because I want to go to here. Okay, all right. I'm conscious of the time. These are the people that have done this: Paul Dunk, Chris Hendrickson, Nathan Kaiser. Nori Shinohara, fantastic scientist. His group has made a huge number of these endohedral species. And Mr. F.T. ICR mass spec, who has revolutionized mass spectrometry. Alan has resolved an oil fraction. He's resolved 105,000 different stoichiometric systems in one run, okay? Just to give you an idea of the fantastic resolution that is now available. Right. It turns out there's been a puzzle since at least, well, the first indication was something about 1923. About 1935, they realized that there was something in interstellar space, something interesting. And here is the spectrum of a star. Okay, and here are a set of absorption lines of something in the interstellar medium, which is thought to be a molecule, okay, or several molecules. My guess is it's several molecules. Not a single one has been identified, okay, none of them. And this is very strange because we've got, millions of compounds, so we've never identified what this thing is, and yet it looks like it's molecular. And they call the diffuse interstellar bands, or the DIBS, D-I-B-S. And here are some of them. And they're very well known. Their wavelengths are known, their frequencies are known. Here are a set of 4 of them. They're sort of famous within spectroscopy and astrophysics. Now, the third man. When we got C60, it just seemed to me interesting that we had to wait till the end of the 20th century, 1985, to discover this molecule of carbon. It was just unbelievable, really. How had it been? Somehow it should have been detected in the 60s, where mass spectrometry was good enough for that. And 1 or 2 people had thought about it, and certainly there were at least one group, Orville Chapman at UCLA, had actually, I think, got an NSF grant to make this molecule. When it came out, I wondered about this, and I wondered whether this fellow in space, these DIB, diffuse bands, was due to C60. And Mike Dura and I suggested a few years ago that maybe C60 would, if it's in space, it will have things stuck to it, okay, such as sodium ions and things of this nature. And if that was the case, there would be a charge transfer band, which would be very strong, because the charge shift from the sodium to C60 would be about 5 angstroms, which is 5 times greater than the standard chromophore, and therefore at least 25 times stronger than the average spectrum, okay? Going by the square of that. And so, in outer space, there we go again, the third man. And I like the film The Third Man, and I'm going to show you a bit of it, okay? Because there's diamond, graphite, and C60. I always thought of it, The Third Man, Der Dritte Mann. And how many of you know the film The Third Man? Yes. Oh, yeah, everybody over the age of 252, yeah, okay, including myself, okay. So I thought C60 is lurking in the back streets of the galaxy like Harry Lime, Orson Welles, in the back streets of Vienna in this film. Okay, so here is a bit of it.
What kind of a spy do you think you are, Satchel Foot? What are you tailing me for? Cat got your tongue? Come on out. Come out, whoever you are. Step out in the light. Let's have a look at you. Who's your boss?
Dat is een tijd nog wel zitten daar los. Soms was het nu wat zijn. Ja, die tippet. Ja, zie mij niet. Dat is zo goed. En de vrijheid is dat niet aan nacht toe en ik ga buiten.
Harry.
En de vrijheid is dat toe en ik ga buiten.
You can see the rest on YouTube. Okay. It disappears. And that's what I thought about this molecule. You know, when you try and track it down, it took us 5 years to track it down. We were pretty sure it was there. It was really tricky. And then, as I say, Kretschmer and Huffman did this beautiful piece of work. We were about, I would say, 2 weeks behind, which is, you know, too bad. But that's the way it is. But then, you know, I thought this must be the case. Well, it turns out it's an amazing thing. The Spitzer telescope came up with an amazing spectrum. Here's this Spitzer telescope, and it came up with this, the white spectrum shown here. You see it? And the amazing thing about that spectrum is that it matches C60. There's a C60 spectrum. But not only that, the clincher is C70, because these are the bands of C70, and they're all there. It's incredible. There's nothing else there. I mean, I don't know about, you know, if you're a chemist, you use infrared for everything. So there's infrared. I mean, how come that the only thing that you can detect coming out of this planetary nebula is C60? So that was surprising. I knew it would be there, but I never thought you could detect it by infrared. This molecule really surprises me every time. So it seems that these stars, out of which all your carbon atoms are made in stars like this, okay? All your nitrogen atoms, all your oxygen atoms are made in these stars by the triple alpha process, 3 alpha particles squeezed by fusion into C12. And so it looks like your carbon were once for C60, some of you anyway. It's just an amazing result. Well, that was exciting. But I thought I'd show you the end of the Horizon film, which was on Nova. And I think Boston is where, you know, you have the Nova programs are made, GBH, what was it, Boston. There was a film made by the BBC on about C60. And I thought I'd show you. And this is Wolfgang Kretschmer, a fantastic guy, and one of the team that actually extracted C60, as I mentioned.
I believe it is there, and it would be rather nice to feel that in fact we were on the right track. There are some interesting features in space, and C60 certainly can fit them better than any other proposal that has been made up to now. I'm a believer, and I think ultimately we'll find that it is there.
But others have said that C60 is nothing like a match from diffuse interstellar bands.
They're wrong.
Thanks a lot. Thank you.
I'd like to open the floor to questions. We do have a student, Charlie, whose major is chemistry, who is going to also take Twitter and Facebook questions. So Charlie, would you like to start with the first question?
Yes. What advice do you have for fledgling scientists who are struggling to find a career path?
Well, I think don't worry about it, all I can say. It's very difficult to say. It's something I will talk about tomorrow, actually. That I didn't go into science to become I went to university to do chemistry because I was quite good at it, but I didn't assume I was going to become an academic. I just did it as best I could, and then things just opened up, and I looked around, and I'm as surprised as anybody that I ended up, first of all, in a university as a professor. Doing as well as I apparently did, because I never knew whether I was going to be any good at it. and with the Nobel Prize, because I just did what I was interested in doing. And at a point where I had to make a decision, I also had opened up a possibility of going to BBC television, educational television, which in some ways I was very close to doing. I think the main thing is just to go into do something that you feel you can really be successful at. I don't say enjoy. I don't enjoy hard work any more than anybody else does. But it's about doing something where it's 2 o'clock in the morning and it's been so interesting that time hasn't mattered. If that's something that you're focused on, solving that sort of problem, then that's something that I think will be pretty successful at. And then that sort of attitude which I think is again something I think I never do a second-rate job. I do, and if I just don't do it. I mean, I haven't got the time of day for this, and it turns out that that's what people are interested in. It doesn't really matter what you do, as long as you do it to the best of your ability. And you usually find someone else who might be smarter than you. There are lots of smart people, much smarter than I am, but they're not as interested in what I'm interested in doing. And I've been, I guess, somewhat fortunate in the sense that I've always been able to do what I've been interested in and not bother about what other people. I mean, the discovery of C60 was a very not mundane, but it wasn't a big problem. It wasn't even exciting to Bob and Rick. They were interested in that as a pilot experiment for another experiment on the diffuse interstellar bands. We had to do that to start off with, but I was interested in this one. Not very interested. I wasn't running around trying to do it, but it turned out it was so surprising. So it's a case of going down the road, and what you discover as things open up. Maybe I think people worry too much about these things. It's about doing the thing at the moment that's as well as you can. That's the only advice. It's about determination and never putting in second-rate. If second-rate effort satisfies you, find something else to do, really, because everybody can find something that they're enthusiastic about, even if it's just drinking a glass of wine, I suppose. I don't know. I'm not being facetious.
We're going to take questions from the audience now. Please, if you are interested in making one, please raise your hand.
Hi, Ron Willey, Chemical Engineering. Don't hold it against me. One molecule caught my interest, and it wasn't buckyball, but the one you had silicon and carbon.
Yes.
Can you explain why a tetrahedral type atom like silicon
yes.
would be bonded the way you show it?
Yes. It's actually silicon stuck in the side of C2. Silicon really doesn't like to be double bonded. The energy, you see, carbon is the exception. So it is pretty happy being double bonded in ethylene, and also it's not too unhappy in acetylene, the propynes. But silicon, to make it double bond is almost impossible, very, very difficult because of the separation of the energies of those things. So it's a very unstable system.
But it's held by two double bonds.
Well, it's really it's not really a double bond, it's really the silicon, the double bond would be two together. So it's really a sort of a triangular molecule. So it's basically a single bonded species to the two carbons at the end. And C3 itself is a very unusual one. C3, although you think it's linear, it's actually has a 48 wave number vibrational bending vibration. 48 wave numbers is 10 times lower than CO2, which is 450 or something like this. So it's actually, carbon is peculiar, more peculiar than you think, and where silicon is much more understandable. So what happens then is that silicon tries to avoid, if it can, double bonded or multiple bonds. And in fact, one thing I was going to do, I was working on carbon phosphorus double bonds, carbon phosphorus triple bonds, carbon sulfur. The next step was to try and create a carbon-silicon double bond, but I was saved from that, trying to do that by C60. Some people have done it, but it's very, very unstable.
Thank you.
Thank you. Another question here?
Yes, please. So my question is that were you, Professor Smalley and Curl, were you collaborators actively or friendly competitors? But more important, after this C60 was discovered, a lot of organic chemists, a lot of pharmaceutical chemists were exploring this as a drug delivery agent.
Yes.
You think that has any chance of success? I was very dubious about it.
I wouldn't think so. I think it could be a delivery of things like radioactive atoms, where you can tag the outside with a sensor molecule and then get it to link to a carcinogenic region, so you could have the atom close to the place where you need it. I think that was not unreasonable. But as a drug delivery, it has to be a bigger one. Well, you can make bigger ones. I mean, this is still an area there are now larger fullerenes with at least 4 or 5 atoms on the inside, but then you've got to open it up. So that's, you say maybe the chemistry of this will go off and you've got a trap door and you can open it up. It's not beyond the bounds of possibility, but I think it looks pretty difficult. Not on drug delivery, but radioactive traces, and perhaps with gadolinium or in NMR, where you can trap a toxic atom which has a high spin for MRI relaxation and stuff like that. These are not unreasonable in the medical area. I think you're right to be skeptical, but that's what science is, to be skeptical about anything other than yourself. But actually you should be more skeptical about yourself than anybody else, because you are the most likely person to mislead yourself, right?
We have another question there.
Thank you very much for your talk. I was wondering if you could also talk about where you got your research funding from, and if you're concerned about funding going forward for science in this area.
Well, none of my 3 major breakthroughs were funded. The carbon phosphorus double bond was not on a research proposal. The discovery of in space, I sent that letter to my colleagues, and in fact, my first trip over to Canada to do this, I paid them away. And the C60 discovery, Margaret, I stole the money out of Margaret's purse to do this. Now, I did get research funding, and I think the situation now is horrific here. I think I agree with you. I think it's something that will come up tomorrow about creativity, because the pressure on young people to get the funding to do what they want is counterproductive for creativity, is disaster. The burden of responsibility is, and I must admit I didn't have that. But I didn't need very much money, and I'll tell you what the system was in the UK at that time. It's changed now. When I went back to Sussex, I was tenured within 6 months of going back. They took me on and that was it. So they couldn't get rid of me if they wanted. Well, they probably could, but they didn't. The first thing to realize that the research students in British University then, but not so much now, if they got a certain degree, they got what's called a quota award from the university. So the chemistry department got 30 of these, and then the student decided who they wanted to work with. And I always got 1 or 2 students, 1 a year. So I had a group on average about 3. I don't need a big group. So I didn't need to find money for them. They had to decide that my research was something they wanted to do. And fortunately for me, over that period, that was it. So that's the first thing. The second thing is, I didn't need any money because I got the government gave the university department enough money so that they could pay some overheads, like £5,000, which was enough in 1967. It went up a little and then went down a bit. So I had overhead money. And then the department already had equipment there which I could borrow, and a friend of mine, a senior scientist, let me use his photoelectron spectrometer. So there was a Raman spectrometer there, and I'd been at Bell Labs doing Raman spectroscopy, and I was one of the first people at the time to do laser Raman spectroscopy of liquids. And so I didn't need any money. I got a student, So my first research papers, nothing at all. And then the only time I had to go, and I did go, was for equipment. So I then went and I had to make a case for a microwave spectrometer, which is, without that spectrometer, I wouldn't be here. Because the microwave spectrometer made by Hewlett-Packard, and I managed, it took me 7 years, 1967, to 1974 to get that spectrometer. So I can wail about the things. You just have to fight it out. But I could still do research with essentially no funding. Now, the problem now is, of course, you get tenure track students, and they have to get an NSF grant. And the situation now is that system was set up so that, say, you had a 30-40% success rate. The success rate now is under 10%, so it's ridiculous. And so the whole system has crumbled and it's falling down, and it's a disaster, and it's totally counterproductive as far as the creative process is concerned. And I think something's got to be done if America wants to actually stay where it is. And I think the point that I was making when I gave a lecture like this is a fantastic audience. But in China, there were 500 wanted to get into a hall with 250. And there were students, Margaret asked them, didn't you, how long have they been there? They were sitting in the front row, said, we've been here since 7 o'clock in the morning to get to a 10 o'clock lecture. We're up against it. These kids are keen. They got quite a lot of money, okay? And I think they don't necessarily have the the right, ethical research orientation, but some of them will have, because there's a lot of them. So I think we have to go back and look at the system now, which is totally broken, because below 10% success rate for getting these grants, you have other places to go. But the point that I'm making is none of mine were on. I mean, if someone has said, I want to discover C60, I mean, they say you're out of your mind. I mean, this is not going to happen. I mean, there's no way that the main thing about the C60 discovery is that it's self-assembled, and it was a total surprise. And there were 6 papers said that it was wrong. There were 6 papers by 4 of the major groups in the field. I can show you all these papers. And so if that had gone for a peer review to these 3 groups, they would certainly have said this is nonsense, it won't be done. But in fact it was, and it took a couple of years to prove that they were wrong. So not only have you've got to fight the peer review, because the peer review is the most ridiculous thing, because you and I know that the real breakthroughs are so unexpected and so unpredictable that it forces you to rethink the paradigm, which is, we had problems. We were pretty sure it was C60. But I thought it was a minute amount. It's coming out of a star. There's some conditions under which nothing else is happening. And in fact, in the case of C60, it's the most stable form of a cluster of 60 atoms. So if you create a system where 60 atoms, that was the genius of Rick's apparatus, that no one had done this before. No one had actually created a cluster of iron with more than 2 atoms. Never been done. But you can now vaporize it, and you get into this condition, you can get, a cluster of 10, 20 or so. When you do the carbon, that's the most stable form of 60 carbonate. Only when you get to millions, now you get the van der Waals interaction between the sheets of the graphene sheets, which now adds to this, and so graphite, which is any old system, right? Then you get below the energy of C60 molecules. So the comment is that I think we have to fight now to change the system. I don't see any way in which young people have something I will talk about tomorrow, which is you need the freedom of mind to be creative. You don't have to worry. You can't be worrying about where the next penny's coming from. And I think it's counterproductive. Sorry to be so negative, but I think hopefully if a lot of us now try to change the system and create an environment for. And we're going to have a meeting at Florida State at the end of this week about this, actually, to what we can do about it.
How about the model in Europe right now?
Pardon?
How about the model in Europe? Is it better than the model?
No, I don't think it is. I think as one that I've been fighting against, although I'm over here in Britain, where now you only get a research student if you're on one of the strategic initiatives. They make a decision. Whereas in the old days, the student would come to work with me if they wanted to work with what I was doing. And it turned out that I was very fortunate always to get about one student a year, which is all I needed. I didn't run a big group. I mean, the maximum size of my group at one time was 5. Usually it was about 4 or 3. One a year was fine. I couldn't think of anything for them, you know. I mean, these people with thousands of papers, you know, I'm thinking, well, I had a hard job thinking of one idea, never mind one. But I think it's important to realize that none of the 3 breakthroughs were on a research proposal.
Any other questions? Yeah.
The future of caged carbon and fullerenes, what do you think remains to be done in the science of caged carbon and fullerenes?
I think you have to be able to create whatever cage you want. I think Larry Scott, who is at, I think, Boston College? He's just retired. I was just talking earlier, you should get him over here because I think he is thinking about, you see, I can't make anything other than C60, C70. C60 is the magic is it self-assembles, and what's important about it was a paradigm shift in solid. We never expected that 60 carbon would just self-assemble into a cage. The point is that there are many other cages, such as nanotubes and things of this nature. And I think to go through with carbon and tap the incredible paradigm-changing technology, nanotechnology, we have to have exact control of structure. Okay? So we haven't got that. We're nowhere near that. I mean, as I was discussing this morning, if you're going to use these, I mean, the nanotubes are wonderful conductors. They're ballistic conductors, so basically there'll be no energy loss, okay? The heat loss in silicon technology is all that, those electrons moving backwards and forwards. That would be gone. But you've got to now solder the nanotube onto your element. Well, you can't use solder, okay? So how can you do this? Well, you might think, okay, here's a C60 molecule. I want to attach a nanotube to this. So that's going to have to be done by organic chemistry. And we're a long way from that. We have no control. Larry Scott spent about 10 years, I think about in 2000, he was able to synthesize C60. And he was the only person who's done it so far, I think, by standard technology. Now, why do that? That is to develop the synthetic engineering, nanoengineering, that will be necessary if carbon nanostructured materials are to sort of achieve anything like the paradigm shifting possibilities. I mean, one thing is that if you could make a bundle of nanotubes, single wall tubes, say, stuck together like straws. You can take a box of paper straws and you can put some weak glue on each of these paper straws, okay? And now you've stuck them together and you can stand on it. Well, you can stand on it anywhere. If you've done this, it will stand up and it will hold you up. If you do that with nanotubes, you will have the material which I don't think will ever be beaten, because the nanostructures you'll have these carbon nanotubes stuck together by weak van der Waals forces, and then what limits materials is the propagation of fractures. Trees have solved this problem by the fibers. The tree is telling you what to do. Can we do it? No. We have to be able to grow these nanotubes, all the same diameter. Okay, so we get the hexagonal packing. We've already got the glue, van der Waals forces, and then you will have a material which will be, I don't know, a sixth the weight of steel and maybe effectively 50 times stronger, because you will not get the fracture propagation across, because the weak bonding will stop that. But we're nowhere near. We can't. We get what we get, you know. So that's, I think, if I were starting on this and interested in it, as I am interested, but I've got other things now, I'm not going to do this, is I would work with an organic chemist to try and make the nanostructures. And so it's just chemistry, and it's a huge, huge task, fantastic area of the future. It's just not even started to get up there. I think it's very exciting.
Yeah, so we are running a little bit out of time now.
And I'd
like to ask the last question. I know that you are passionate about your research. It's very obvious. I think it's not a coincidence that you discovered this very important molecule. But I also understand that your passion is about education.
Yeah.
And you made this comment that once upon a time you worked as an apprentice in your father's factory. And you commented that set you up for the rest of your life as a problem solver. So whether there is a relation or not to this, I'd like to ask you if you were going to make one comment on education, and I know you are going to talk about it tomorrow, for us educators, what would it be?
Well, I think it's to recognize that when I was at school, I spent probably 2 days a week in the laboratory in high school.
Yeah.
And that's not possible anymore. I mean, I was working in, if I wasn't in, because I just did maths, physics, and chemistry from the age of 15 to 18 before I went to university. And so we had lecture, some lessons, but then the rest of the time was actually hands-on chemistry, hands-on physics. And I think the apprentice system, I think what you have here is interesting. I think you have a course where you go out into industry.
Yes.
I think that's actually probably one of the most important things that I've learned since I've been here. Yeah. And I think basically hands-on. If you saw that little boy that Margaret took the photograph of, that kid was totally engrossed in making something with their hands. And I had Meccano, which you call erectus. Well, you stole it, like you stole the country. But it called it. I had hands-on things, and I think I made a lecture like this to the British Engineering Society Institute of Engineers, and I asked how many had Meccano, which is erectus. Said it was 99% of them had Meccano. That it's not Lego. This is nuts and bolts. Putting a nut and bolt together is one of the greatest skills that we have. Yeah. And tightening that bolt sufficiently tightly that it will stay together, more or less, but not so tight that you can't undo it. All right, like the guys who put the nuts on the wheel of my car. When you know, I don't know how many of you have been on the motorway and you can't get the bloody nut off, right? You know, you've been through it. This guy never had Meccano. You know that. You know, I actually always have another lever. A pipe, but when I came to this country, I forgot that in the back of my car in England, I've got a pipe which gives me, if I give me a lever and I'll move the car. No, give me a lever, I'll get the nuts off the wheel of my car. I've got one in there, but I haven't had a puncture since, so there you go. Absolutely vital that kids put things together with nuts and bolts. Not only that, it gives you a feel for materials, aluminium nuts, plastic nuts, steel, copper, brass. That sort of hands-on feeling for this, and even to this day, I get a tremendous kick on solving the problem, putting a nut on, which is difficult, and not misthreading. That's engineering for you, I think.
Very good. Thank you very much. In closing, I'd like to thank the Center for High-Rate Nanomanufacturing, who has been hosting Professor Kroto and his wife, and announce that tomorrow there will be a lecture by Professor Kroto on education, so you are all invited.
Well, it's actually on science, society, and education.
Science, society, and education. Sorry about that. 4 o'clock right here. Professor Busniena, as you know, is leading the center and will lead the lecture. So thank you very much again for this really very fascinating talk.